Welcome to CyberEd's presentation of atomic structure. In this program, we will clearly define the concept of an atom, show how the structure of an atom has been determined through experimental investigation, and learn how quantum theory has shaped our conception of that structure. We will discuss the various ways the particles in an atom can be arranged and the implications of the instability of some atoms. We will use some of the ideas and definitions presented in the program Introduction to Chemistry. You might want to go back and review that program before starting this one. Everything is made up of elements. Elements can combine to form compounds, and compounds are usually found in mixtures. All of these terms help us define what we call matter. In this program, we're going to see what elements are made of. Long ago, some people made good guesses about elemental composition. The ancient Greek philosopher Democritus reasoned that there must be a smallest individual particle of an element that still has the characteristics of that element. He called the smallest particle an atom, the Greek word for indivisible. In the Middle Ages, Galileo, the astronomer, knew of Democritus' thinking, and he stated his belief that the creation of a new compound must involve rearrangement of these atoms. In 1803, Dalton proposed his atomic theory of matter. He stated that elements are composed of tiny particles called atoms, and that all atoms of a given element are exactly alike and differ from atoms of other elements. He further stated that atoms cannot be created or destroyed, whether by lightning, heat, cold, or pressure, and that compounds must be composed of atoms in fixed proportions. This set of postulates, or hypotheses, was essentially correct, but it took scientists almost 100 years to prove it. Around the year 1900, scientific studies finally confirmed that atoms are indeed the smallest elemental particles. More recently, physicists have actually photographed an atom. Not with an instamatic, to be sure, since 1,000 atoms would fit into a single wavelength of visible light, but using a device called a scanning tunneling microscope. By observing the way that a very fine-pointed electronic probe moves up and down as it crosses a copper atom, a topographic map of the surface of the atom can be produced. Just like Democritus, Galileo, and Dalton, the scientists exploring the structure of the atom were faced with the task of understanding something they could not see. However, they could study the behavior of atomic particles subjected to electric fields and magnetic fields. And from this, they concluded that there were both positive and negative particles in an atom. Also, they could determine how much deflection occurred when larger atoms are bombarded with smaller atoms. And from this, conclude that most of the mass of the atom was concentrated in a tiny area near the center. On the basis of these experiments, scientists were able to create a series of hypotheses, or possible explanations, about the actual structure of the atom. The hypotheses describe the atom as being mostly empty space, with a positively charged dense central core surrounded by a negatively charged shell of particles. Additional experimental work confirmed and refined this hypothetical atomic structure, giving rise to the planetary theory of atoms. This theory suggested that the structure of an atom could be compared to that of our solar system. A large, dense central core like the Sun, surrounded by small orbiting objects like planets. Although the planetary theory presents a convenient visual picture of an atom, it has some problems. For instance, classical electromagnetic theory says that particles of opposite charges will be attracted to one another, and particles of like charges
will repel one another. Why then don't those positive particles in the core fly apart? And why aren't the negative particles attracted toward the positive core? Furthermore, why do the different orbits contain 2, 8, 18, or even 32 negative particles at approximately the same distance from the core? Unlike atoms, planets don't have charges and don't cluster in their orbits, so a better model of atomic structure was needed.
The discovery of the neutron, a particle similar to the other particle in the core of the atom, but having no charge, answered the question about what keeps the core from flying apart. Neutrons, through a series of complex interactions, help to actually hold the positive particles together. As long as we're naming things, the positive particles we've shown in red are called protons. The negative ones in yellow are electrons. And the core of the atom is called the nucleus. Collectively, protons and neutrons are called nucleons. Classical electromagnetic theory says that particles of opposite charges will be attracted to one another, and particles of like charges will repel one another. Yet, as previously mentioned, negative electrons don't spiral into the positive nucleus and disintegrate, and multiple numbers of negative electrons can occupy the same orbit around the nucleus. These problems were addressed by Planck, Einstein, and Bohr during the first 2 decades of the 20th century, when they developed the quantum theory of the nuclear atom, often called the Bohr Model. The Bohr Model of the atom hypothesizes that as long as the electron moves with a certain minimum speed and stays in a certain fixed orbit, the orbit will remain stable, and the electron cannot be sucked into the nucleus. You might compare this to your spinning a light stick on a string around your head. As long as the light stick keeps moving at a minimum speed, the string stays taut. But if the light stick slows down, it drops out of its orbit. The Bohr model also accounts for multiple electrons occupying each of these fixed orbits. This is explained more fully in the program entitled Electronic Structure, which goes into the details of quantum theory as it applies to electron orbits. Although quantum theory resolved many of the aspects of atomic structure, there were some troublesome discrepancies between the theory and experimental observations of particle behavior. In the 1920s, de Broglie postulated that protons, and especially electrons, behave the way light does. That is, they possess both wave-like and particle-like properties. The existence of this duality remains one of the puzzles of science, but it certainly helps explain some of the chemical and physical properties of atoms. Working from de Broglie's postulates, Schrödinger developed a model of the atom that incorporated both the particle and wave components. Our atomic displays are based on the Schrödinger electronic orbitals, but we will explicitly show the Bohr electrons in those orbitals. For our purposes, we will consider atomic particles to be just that, particles. But we will show the shapes of electronic orbitals in accordance with their wave-like behavior. As mentioned earlier, atoms and their component particles are quite small. For comparison, we've superimposed a model of a neon atom onto the solar system by expanding the atom until it has the same diameter as the solar system. As you can see, the atom, like the solar system, is mostly empty space. But you can also see that the electron orbitals are nothing like planetary orbits. Note also that the weight of the electron is only about 1/2000th of the weight of a proton, although both have about the same diameter. An atom in its elemental form is electrically neutral. That is, It always has exactly as many electrons as it has protons. The chemical properties of an element are determined entirely by the number of electrons that surround the nucleus. An atom can gain or lose one or more electrons to become an ion, which is the name we used for a charged atom. Since the number of electrons has changed, the chemical properties of an ion differ from those of the corresponding uncharged atom. However, the element that the ion represents remains the same, since the identity of a particular atom is determined solely by the number of protons. We refer to the number of protons as the atomic number of the element. In the program Introduction to Chemistry, we showed how the elements are arranged in the periodic table by increasing atomic number. Although the atomic number, the number of protons in an atom of a particular element, is fixed, the number of neutrons is not. Atoms of the same element that have different numbers of neutrons are called isotopes. The number of neutrons does not affect the chemical properties of the element, since those properties are determined entirely by the number of electrons. Although the isotopes of a particular element have differing numbers of neutrons, they have the same number of protons, or atomic number. In order to distinguish among isotopes, we need to measure something besides protons. Total number of nucleons, for instance. If we take the sum of the numbers of protons plus neutrons, which accounts for practically all the mass of the isotope, we get its mass number. This number is used to identify a particular isotope of an element. By agreeing that carbon-12, with 6 protons and 6 neutrons, is defined as having a mass of exactly 12, chemists have established a scale of relative masses for each isotope. These masses are called atomic weights, and they are essentially identical with the mass numbers. Note that the mass number does not uniquely identify the element. Both hydrogen-3 and helium-3 have the same number of nucleons, and thus the same mass number. But they have different atomic numbers, and thus are different elements.
Although the mass number of an atom is a whole number, the atomic mass of an atom is, in fact, fractional. You can get fairly close to calculating the atomic mass of an atom by adding up the masses of all the protons, neutrons, and electrons in that atom. However, energy is released when the nucleons bind together, and since energy and mass are related, some of the mass of the atom is lost as energy when the nucleus forms. Therefore, an accurate value for the atomic mass cannot be calculated by simply adding together the masses of the individual subatomic particles, but rather must be obtained by experiments performed on the individual isotopes. Notice that the atomic mass, as reported on the periodic table, is slightly different than the atomic mass for either isotope of boron. This is because the atomic mass, as listed on the periodic table, is actually an average, calculated from the atomic masses of all naturally occurring isotopes of that particular element. The atomic mass value, as provided by the periodic table, is referred to as the average atomic mass.
Quantum theory states that only certain ratios of neutrons to protons in the nucleus can exist. Too few or too many neutrons will cause the nucleus to spontaneously decay. That is, it will eject one or more particles from the nucleus in order to achieve a stable ratio of neutrons to protons. We've shown a plot of neutrons versus protons for all of the stable isotopes of all the elements you can see a very narrow belt of stability that favors having a few more neutrons than protons. Isotopes that are outside the belt, and even some that are inside, decay in such a way as to get closer to the center of the belt. And the farther the isotope is from the belt, the faster that decay will occur. Elements that contain these unstable isotopes are described as radioactive, and chemists handling such elements must take special precautions to avoid the high-energy emissions that accompany the decay of these radioactive isotopes. Depending on their neutron-to-proton ratio, radioactive isotopes decay in different ways. If the nucleus has fewer neutrons than protons, the nucleus either emits a positive particle, called a positron, or captures one of the orbital electrons. In either case, a proton is effectively converted to a neutron, and the atom's atomic number has decreased by 1. If the isotope has more neutrons than protons, but still has too few neutrons to be in the belt of stability, or if it simply has too many nucleons to be stable, it ejects a particle composed of 2 protons and 2 neutrons, called an alpha ray, which ultimately captures 2 electrons to become a helium atom. The remaining atom has decreased its atomic number by 2 and its atomic mass by 4.
If the atom has too many neutrons, the decay usually involves the emission of an electron, called a beta ray, from the nucleus. Since the nucleus contains no electrons, where did the ejected one come from? An unstable neutron can escape not only the nucleus, but the entire atom. You might have noticed previously that the mass of a neutron exceeds the mass of a proton by almost exactly the mass of an electron. Since the atom now has 1 more proton, it has become ionized, and it needs to capture an electron so its electrical charge stays neutral. Notice how the atomic number has increased by 1, even though the mass number stays the same. Some radioactive isotopes initiate a whole series of alpha and beta decays, such as the decay of uranium-238, which eventually produces a stable isotope of lead. Some isotopes, especially the heaviest ones, show another type of decay. These elements actually eject a neutron from the atomic core. This expulsion is accompanied by a burst of energy, called a gamma ray. Gamma rays may also accompany very energetic alpha and beta decay processes. The released neutron is highly energetic, and it may strike other unstable isotopes, which in turn may strike other unstable isotopes, and so forth. This phenomenon is called a chain reaction. Another term for this self-destructive process is fission, the driving force in nuclear reactors and the atomic bomb.
The reverse of the destructive fission process is called fusion, where 2 nuclei combine to produce a single nucleus. Beams of protons, deuterium atoms, and helium atoms are commonly used to generate fusion reactions. Almost invariably, the new nucleus weighs less than the sum of the 2 nuclei that join, and the difference in mass is converted into energy, as Einstein explained in his famous equation that calculates the amount of energy created to be the loss in mass times the speed of light squared. Fusion powers the sun, and a hydrogen, actually deuterium bomb, is a fusion reaction. In a scientific equivalent of throwing rocks at a rock pile, physicists use particle accelerators to hurl nuclei at other nuclei. Their purpose is to produce nuclei that are far from the belt of stability and determine from the way that they decay what actually happens inside the nucleus. By choosing the proper set of rocks, physicists can even create new elements. All of the elements with atomic numbers higher than plutonium were built in this way. Most of the recently created ones are so unstable that they decay in fractions of a second. Isolating even a few atoms of them long enough to study their properties has been one of the highlights of modern chemical accomplishment. In this program, we started with the model of the atom as a simple billiard ball. We then explored the Planetary model, where a central positive nucleus is surrounded by fixed orbits containing fixed numbers of electrons. This model was supplanted by the Bohr Model, where the various component parts of the atom behave as quantum particles instead of following classical electromagnetic theory. Finally, we arrived at the Schrödinger model, where the electron behavior is expressed by quantum wave equations that describe variously shaped and numbered electronic orbitals. We've also looked briefly at characterization of atoms in terms of their atomic weights and atomic numbers, and the effects of atomic instability on the structure of the atom. The next program in this series takes a detailed look at the influence of electronic structure on chemical properties